And he can test whether those numbers are equal by XORing them together and checking what the value of that is. But binary operations are associative and commutative. This is exactly identical to just XORing all of the numbers together and seeing if they're 0. So Patrick doesn't care how the numbers are, or how the candy are arranged between different piles. That's irrelevant to whether he's going to be happy. You can just XOR all of the numbers together, see if it's 0. If it's 0, he'll be happy no matter how they're arranged. And then you just pick the smallest one. Sean gives that to Patrick. He's happy, and Sean takes all of the rest of them. And so it's very easy to write part D. It's actually a simpler solution than the complete search model. All right. So congratulations to everyone who solved that. Pretty much everyone got the right answer and solved the end part, although, again, a lot of people were struggling with the complete search solution. And the thing I really want to get you to get about that is that bit masks are a useful way to loop through subsets, and they're going to be way faster than basically any other approach you can come up with. Okay, so that's it for the homework. Congratulations to everybody who participated in the ICPC regional qualifier last Saturday. I think about half the class was there. Most of you did quite well. One thing I did want to note about that, because I saw a lot of people making this mistake, is that there were, what, about 10 or 11 problems total. And I think about half of the people that I saw competing started in immediately on the first problem. And if you actually took the time to go through and read all 11 problems before you got started, there were at least 2 problems that were a lot easier than that one. And so you want to make sure in general, when you're competing in these programming competitions, you want to go from easiest to hardest, both because you're more likely to solve the easy ones, and because, particularly in the ICPC, you get scored on how quickly each solution goes in. So if it takes you 2 hours to solve the hard one and you can solve the easy ones in 10 minutes each, and there's 3 easy ones and 1 hard one that you have time to solve, you'll get a better score if you solve the easy ones first, because then they'll be done earlier, rather than if you wait until after solving the hard one. So it is very important when you're solving lots of problems to make sure you've picked the right one to start on. All right? And so that was, I think, the biggest problem that I saw. And then past that, I think everybody who was there solved at least 1 or 2 problems. So great job. For those of you who weren't there, we're going to have, again, 1 or 2 more of those practice competitions that are going to be required for you to pass the class. All right. So let's move on to today's topic. So this week we're going to start on graph theory. And this is actually the only topic that we're going to take multiple weeks to cover. Has anybody done any graph theory in any of their other classes? Any graphs? All right, so we've got a couple people that are new. So again, we're going to cover this for 2 weeks, and there's 2 reasons for that. First of all, graphs are really important. There's a lot of different interesting and useful problems that you can treat as a graph and then solve them using standard graph theory algorithms. It may not always be the most efficient, but it'll work. And so being able to turn a problem into a graph and then solve it using these known graph algorithms is a really useful skill that you'll use all the time. And secondly, graphs are kind of complicated, and so it's going to take a lot of time to cover everything. There's a lot of different ways to organize graphs. There's different kinds of graphs. There's different ways to store graphs in the computer so you can work with them. And there are a ton of useful and important graph algorithms, some of which I'm still not going to be able to cover, even with taking 2 weeks. Okay, what's a graph? At the most basic level, we'll take a graph G And that is a collection of vertices that we'll call V and edges that we'll call E. So vertices are just elements in the graph. They can be, they're usually indexed from 1 to whatever, while edges are pairs of connected vertices. So we can have some edge, x, y, and that's in our graph. So what we use graphs for are as a way of representing the relationships between different elements that we're interested in. So element A and element B, or element X and element Y, are connected in some way. There's some relationship between them. So maybe we want to treat the vertices as cities, and then the edges are roads between these cities. And then that graph would represent a road network. Or maybe the vertices are going to represent people, and the edges will represent relationships between the people. And then we'd be modeling a social network with the graph. But in general, when we talk about elements, we're going to talk about, when we talk about graphs, we're talking about elements as vertices and edges as relationships between those elements. This is a very broad definition, and that broadness is what makes it useful, because we can model lots of different kinds of problems in that way, reduce them to a graph, and then solve them using the same kinds of algorithms. Okay, so let me draw a sample graph. Usually when we draw graphs, we'll draw a little circle with the name of the element in it. That's a vertex. So we'll have the vertices be the numbers 1 through 5. And then we'll draw lines between them to mark edges. So 1, 2, 3, 4, 5. And then I had 2 and 5. Okay? So here's a simple graph. There's 5 elements, and there's 7 edges. So we've got 1 and 2 are connected, 1 and 5 are connected, and so on and so forth. So the first step when we're trying to solve any problem by modeling it as a graph is that we need to correctly define the kind of graph we're going to treat it as. So what are the vertices going to represent? How are the edges going to be defined? What's the general shape of the graph? How is the graph structured? And there's a number of different variations of graphs that will be treated differently when you go and solve them. So there's some algorithms that only work on particular kinds of graphs. So the first distinction I want to talk about are directed versus undirected graphs. Okay, so like I said, edges are pairs of connected vertices. So suppose we have some edge, x, y, that shows up in our graph. That says x is connected to y. If, when this edge is in the graph, the reverse edge is also in the graph, that means we have an undirected graph. That means the relationships that these edges are modeling are symmetric, so that if x is connected to y, then y must also be connected to x. So that's true for some relationships, but it's not true for all relationships. So suppose we're drawing a social, this is going to represent a social graph between employees at your company. And maybe we want the edges to represent whether those people are working on a project together. So we've got an edge here, and that says, oh, 1 and 2 are working together on something, and 1 and 5 are working together on something, and so on and so forth. That's a symmetric relationship. So if 1 is working with 2, then 2 is also working with 1. You can't have them separately. But if we instead want to draw maybe the hierarchical network at the company, where the relationship is, x is the boss of y, that's not a symmetric relationship. If x is the boss of y, that doesn't mean y is the boss of x. And so that is going to be a directed graph. And when we draw a directed graph, we mark that by drawing little arrows on the line. So this says, so if we're drawing this as a hierarchy, this might mean we could draw in little arrows like this, and that would say, okay, 1 is the boss of the whole company, and he's in charge of 2 and 5. And then 5 is in charge of 4, and then 4 is in charge of 3, and this is our intern at the company. Okay? So this is a directed graph. Every edge has a direction associated with it. And so most of the algorithms we're going to discuss are meant to work on undirected graphs. But some of them also work on directed graphs, and there's some algorithms that are specifically designed for working on directed graphs. And I'll talk about a specific subset of directed graphs that are very important in a bit. So the another important distinction is weight. Let's take our same graph, we'll turn it back into an undirected graph, we'll remove the little arrows here. And instead of thinking of it as a social graph, let's think of it as a road network. So maybe all of these elements are cities in Missouri. So this one here is St. Louis, this is Kansas City, this is Springfield, can have this be Columbia, and this will be Jeff City. Okay? And this might be, a map of which cities are connected to which other cities by roads. So St. Louis, there's a road between St. Louis and Columbia, and there's a road between Columbia and Kansas City. But there's no direct road that goes from St. Louis to Kansas City without going through Columbia. Now, depending on what we want to do with the graph, this might be sufficient. So if we only want to say, can you drive from St. Louis to Kansas City on these roads, then this is fine. We can look for a path along edges from node 1 to node 3. But more likely what we're interested in is maybe finding the shortest path. Maybe we want to look at the distance along each road and find the shortest one. In that case, what we can do is assign weights to these edges, where the weight is whatever we're interested in. So if we're interested in distance along a road network, that might be, say it's 50 miles here and 55 miles here and then another 40 miles here or something like that. And then if we want to look at how long it is to drive or how far it is from St. Louis to Springfield along these roads, we can walk from here along this path, add up the weights, and that gives us the value. Or maybe we want to look at driving time instead of road distance. Then we can replace these weights with how long it takes to drive along those roads from here to here. So any time where there's something associated with that relationship that we can treat as a number. So on a road network, it might be distance or speed. In a social graph, it might be something like how strong is the relationship between these people? Are they acquaintances? Are they friends? Are they really close friends? And you can model that as a number. So anytime we have some weight associated with it, or some value associated with the edge, we want to use a weighted graph. Okay. So the next distinction, let me erase these again, is simple versus non-simple graphs. And this is pretty straightforward. The basic problem is that when you're doing analysis of graphs, there are a couple of kinds of edges that cause problems. You can get into loops in your, you need to special case them when you're writing algorithms. And so they're tricky to deal with. One of them is called a self loop. And that's where a vertex is connected with itself. It has an edge from itself to itself. And you can see how that might cause a problem. If you're trying to look for a path from 3 to 1, then you could go from 3 to 3 an infinite number of times and then go to 1, and that's a path. That's a valid path. But that's probably not a path you're interested in, and so that can cause problems if you're looking at that. The other kind of edge that causes problems is called a multi-edge. And that is where you have two edges that are identical. So you've got one path from 2 to 3, and then here we've got a second different path from 2 to 3. And again, that's going to cause problems in a lot of different algorithms. So a simple graph is one that doesn't have any of those. You don't have to worry about self-loops. You don't have to worry about multi-edges because they're not there. And that's simple versus non-simple. There's also, usually if you have a non-simple graph, what you'll want to do is replace it with an equivalent simple graph. So we can take one of these multi-edges and put in sort of an auxiliary node or vertex right there that's in the middle of that. And now, with that auxiliary node, this isn't a multi-edge anymore. These are distinct. And you can work with this normally like you would. And for a multi-loop, you can do the same, or for a self-loop, you can do the same thing, except you need two edges to do it. And so usually if you've got a non-simple graph, you want to modify it by adding these auxiliary nodes so that it is simple, so that you don't have to muck up with the algorithms, so that everything works properly. All right, so that's something to keep an eye on. Non-simple graphs can be tricky, and you generally want to avoid them. So the last important distinction is whether there are any cycles in your graph. So this is cyclic versus acyclic. So we want to know, are there cycles in the graph? What's a cycle? A cycle is a path along edges that leads from some node back to itself. So in this case, there are a bunch of cycles. So we can go from 2 to 3, 3 to 4, and then 4 back to 2, and that's a cycle. Or we could go from 1 to 2 to 5 back to 1. That's a cycle. Now, if we were working, again, with the hierarchical graph that I drew earlier, there actually weren't any cycles in that, because all of these were directed. So, and there's no way to get from any node back to itself. So again, a cycle is any path that leads from an element back to itself. So this is useful because there's a couple of specific types of graphs. So one type of graph, which is a acyclic connected unweighted graph. So an acyclic connected unweighted graph, or sorry, undirected graph. My bad. Undirected. So we know what acyclic and undirected mean. What connected means is that there's always some path from one node to the rest of the graph. So there's not another node up here called 8, that there's no path from that node to the rest of it. So it's connected. And what this is a tree. All right? And everybody's seen trees before because we talked about a specific subset of trees 2 weeks ago called suffix trees. And suffix trees are a particular kind of tree. And trees are a particular kind of graph that have no cycles. Everything is connected to each other. There's no separation. And there's no direction. So let's look at a suffix tree example. So the root of a suffix tree is just an empty node. And then you have children there that are characters. And those characters give you information on the strings that are stored in the tree. So maybe this is AA. So this, for example, contains the strings AA, BC, and BD. How did I come up with those 3 values? Where did I get AA as a string that's in this? Can everyone see this? Do I need to write it bigger? So each terminal node represents a string, and the path from the root to that terminal node spells out the string that node represents. So right here, we're walking from the root node to A to another A. So this is the string AA. For right here, we're walking from the root node to B to D. So this stands for BD, and so on and so forth. And the reason why you can do that with a tree is a particular property of a tree, which is that there's only one path between any two nodes. If there were multiple paths between any two nodes, so suppose we had something like this, where here we've got a C here, and that points back to the A. Then we've got a node here, this A, that has two different paths from it back to the root. And so there's no way to uniquely identify the string that that represents. And if you look at this, you'll see that there's a cycle there now. And so if we have an acyclic graph, that guarantees that there's always a unique route from any node to any other node. All right? So trees are a particularly useful kind of graph that, again, are acyclic, connected, and undirected. So if you have some random graph and you can prove that it's undirected, connected, and that there are no cycles, it's a tree. You can pick a vertex as a root and use all of your tree algorithms on it, and it works just fine. OK? So that's one particular kind of graph. The other useful kind of graph is called a directed acyclic graph. And this is usually just abbreviated DAG. So if you see somebody talking about a DAG, that's what that stands for, is a directed acyclic graph, just like our hierarchical map right here. And so this is a particularly useful structure for storing priorities. So suppose you've got, so like for our hierarchy, the person who is node 1 has priority over the person in node 2. And because it's acyclic and it's directed, you can say unambiguously for any two pairs of nodes which of them has priority, which of them is the boss in some way of the other one. Maybe it's directly, or maybe there's a path from that one to the other one that says this person is in charge of this one. Or maybe you want to store it as a scheduling problem. So suppose each node represents a task, and the edges say task 1 has to be done before you do task 2. There's some requirement that something from task 1 is required for task 2. And then task 2 is required for task 3. A very, very common problem on directed acyclic graphs is called topological sorting, which we'll talk about next week. And the idea for that is to take a graph like this and come up with an order of the elements that follows all of the constraints. So in this one, for example, that might be do task 1, and then task 2, and then task 5, and then 4, and then 3. And that's an order where every task has its prerequisites done before it comes up. And that's called a topological sort. And again, we'll get to that the details of that next week. OK, so that's our graph classification. Let's talk about graph storage. There are a couple of different ways to represent, yeah?
Why can't a tree be direct?
So a lot of times you'll see directed graphs drawn as trees, as asymmetric parent-child relationships. And that's valid, but it's not really a tree, because technically, if you can't actually go from a child to the parent, there's no path from that child to any other child, because you can't travel this way. So usually when you're dealing with trees, they're actually stored internally as undirected graphs, and you keep track of which one is the parent and which one is the child. OK. All right, so we're going to talk about ways to store graphs in the computer. There are a couple of different ways to do this. So the most basic level, and I saw a bunch of people implement these when we were talking about suffix trees, is you store each node as an instance of an object. So maybe you'll write a class called node, and that's going to contain, it's going to have a label that says, for this one, this might be element 1, and then it'll have a list of edges, where this is pointers to other node objects. So node 1 would have a pointer to node 2 and node 5 in a list. And then node 2 would have a pointer to nodes 5, 4, and 3 in a list. And so this works fine. This is a perfectly valid way to do it. But it's very memory intensive because you have to allocate space for each object independently. It's pretty slow to work with. There's no way to directly find whether there's an edge between any two elements other than walking to that particular object and checking in its list. And so it's kind of slow. So in general, this is not the best approach to take. It's OK for small graphs. So if you've got a 5-element, 7-edge graph, that would work fine. But for larger graphs, it's going to slow you down. So let's talk about an alternative. The next method is called an adjacency matrix. So what we do is if we've got some graph with v vertices, then we allocate an array that's v by v. So if we're going to represent this graph as an adjacency matrix, we'd have a 5 by 5 array. 3, 4, 5. And then anytime there's an edge in your graph, I'm going to go back to the undirected graph here. Anytime there's an edge in your graph, the element in your matrix is 1. So there's an edge between 1 and 2, and between 2 and 1, so those are 1s. And anytime there's not an edge, you put in a 0. So for this graph, here is the matrix representation. 0, 1, 1, 0, 1, 1, 0, 1, 0. So that's the matrix that represents this graph. Anytime you see a 1, you can say, there's an edge between those guys. And this has a couple of advantages. First of all, it's really fast to see whether any two particular vertices are connected, because if you want to know if 4 has a connection to 3, you can go in and it's a simple lookup to grab it. You can say, yes, that's a 1, there's an edge there. It's also a very simple way to represent weighted graphs. If there's a weight associated with each edge, all you have to do is say, OK, well, maybe this edge has some weight 10. You just change that to a 10 right there. And you change all of these values to numbers that represent the weight of that edge. However, the downside is that it takes a lot of memory to store the matrix, particularly for sparse graphs. So a sparse graph is a graph where there's not as many edges as there could be. So the maximum number of edges is v squared. But for most graphs, there's not really v squared total edges. So for this one, there's 5 elements, but there's only 7 undirected edges. And so because we're allocating v squared space for a large sparse graph, most of those elements are going to be zeros. And it's really just wasted space. So the best way to do it, almost always, if you're not using an adjacency list, you should have a good reason why not, is, again, an adjacency list. And the way this works is it's a list of lists. So we start off with a list of length v. So we've got with elements, or with keys 1, 2, 3, 4, 5 for this guy. And then each of those has a list associated with it that tells you what edges this guy is a part of. So for 1 is connected to 2 and 5. So that has a list 2 and 5. 2 is connected to 1, 3, and 5. So that has a list 1, 3, 5. Oh, 4 and 5. 4 and 5. And then the same for all of the rest of them. Let me fill these in real quick. 2, 3, 5, 1, 2, 4. So this also gives us all of the information about our graph that we need. And it's a lot more memory compact. It's not quite as fast to find any particular edge, because if we want to know if there's an edge between 2 and 4, we have to go here and then search in this list for 4. So it's a little bit slower. But the space is sufficiently small enough that this is usually what you want to use. If you don't use an adjacency list, you should have a good reason for not using it. Yeah?
How is this different from just using the nodes that you, like, making a node class and storing the nodes that it's connected to?
Well, so suppose, OK, so when you're doing that, usually what you're going to, how you store the graph is with a pointer to some root node, right? So you would have a pointer to 1. And if you wanted to look at something about 3, you would have to start at 1, but then you'd have to get to 3 somehow. So you could do that by storing pointers to all of them, which is fine, and then storing a list. But then you've just recreated an adjacency matrix, except with an additional object wrapping everything, which is just extra memory that you don't actually need when all you really need is a list of lists. So if you implement it correctly, it is exactly the same thing. It's just, a little wasteful. And if you don't implement it correctly, it's going to be a lot slower if you don't actually have connections to everything. OK. All right, so that's graphs. Let's start talking about some actual graph algorithms. So the most fundamental graph theory problem that you'll see all of the time when we're working with graphs is graph traversal. So we take a graph, we have a starting vertex that we want to start from, and we want to systematically explore the graph until we've reached every possible vertex we can from our starting position. So if we start at node 1, we want to go through and explore all of the other nodes here until we've reached every possible node. OK, so there are 2 things you want to keep in mind when you're doing a graph traversal. First of all, you want to make sure you're being efficient. We don't want to revisit nodes that we've already visited. So if we've been to 1 and 2, we don't want to go back there. We don't want to keep revisiting them, because that's wasting time we could spend instead visiting new nodes that we haven't been to yet. And then secondly, we want to make sure we get the correct answer. So if we write a program and we say, OK, I've been to 1, 2, 4, and 5, but then we end before we get to 3, then we've made a mistake. We haven't sufficiently explored the graph. There are connections that we haven't gone through. So we need to be correct, and we need to be efficient. All right, how are we going to do that? Well, if we want to make sure that we visited everything, and we want to make sure that we don't revisit the same thing, the obvious thing to do is to create an array of Booleans that tells us whether we've been to each node before. So we'll start it off allocated with all false elements that says, OK, we know there's 5 elements, and we haven't been to any of them yet before we start. And then to make sure that we visit everything we could, we're going to create another data structure. And I'll get into exactly what that data structure is going to be, that marks nodes that we could visit, but we haven't visited yet. So these are nodes we know how to get to, but we haven't actually gone there yet and explored them fully. And this is how we're going to start off. So we're going to start off our array of visited elements as entirely false, because we haven't been anywhere yet. And we will start off our available data structure as empty, because we don't really know where we're starting yet. OK. how do we use these structures to comprehensively walk through the graph? So first, we pick a starting vertex. Maybe I'm going to start with node 1. That's going to be where we're going to start from. And then we set its flag here in the visited array to true. And we go into the available array, and we fill in all of the edges from 1. So we've been to 1, and now that we're at 1, we know how to get to 2 and 5. So now we've got stuff in the available array. And then we repeat the following process. Let me switch to black. First, pick a node. We've got a list here of nodes that we know how to get to, 2 and 5. So we pick one of them. How we pick that is going to change the way we traverse the graph. And I'll talk about how that works later. So right now, we're just going to say, OK, maybe I'm going to pick 2. And then we repeat this. We set it as visited. So now we're going to walk to 2. We'll say, OK, I've been to 2 now. We'll look in the adjacency list. So now here's 2. Here's our list of nodes that are connected to 2. And add adjacent nodes to the available list. And there's a caveat here, which is that we want to make sure we don't add nodes that we've already been to, because we don't want to waste our time going back to them. So in this case, we've got 1, 3, 4, and 5 that we know how to go to. So we've removed 2 here. And we can go to 3 and 4. So we add those in. We could go back to 1, but we've already been there. So we're not going to waste our time. OK? And then we just keep looping through this. So now we go back. We say, OK, I'm going to pick another node. I've got 3 to choose from, 3, 4, and 5. I know how to get to all 3 of those. So you pick one. You go to it. You set it as visited. You look for any new nodes that are available, and you put them in your list. And you keep looping through that until there's no more nodes left in your available list. And that says, I've explored every node I possibly could from this starting node. I've gone everywhere. OK. Let's talk about this first bit. How do you pick which node you're going to start from? Let's suppose that for our available list here, we're going to use a queue. All right, we talked about this, what, second week of class? How does a queue work? Somebody tell me how a queue works.
First in, first out?
Yes. So anytime we pull an element off of the queue, we're getting the oldest element, the earliest one that was pushed onto the queue. OK? So let's walk through how that algorithm works when we're using a queue for that, starting from position 1. So we're going to draw what's called a traversal tree of the graph. So we're going to mark the root node as 1. And then we're going to connect each node as we walk from that particular node to the next one. So we start at 1. What gets pushed into the queue? Somebody? 2 and 5. OK. And we've marked it as true. Let me change this here. All right. What gets pulled off of the queue as our next node? 2. So we draw from 1 to 2. Now we've been to 2, and we've removed it. What gets pushed onto the queue?
3 and 4.
Yes. So now we've got 5 up here, and 3 and 4 get pushed on. What gets pulled off? 5. All right. Fill out and tell me how to finish up this tree.
OK, so you're gonna pick one of the nodes.
So we've been to 5 now.
Yeah.
What's next?
So So you're going to pull 3.
Going to pull 3 off. And where did we get that 3 from?
We got the 3 from the 2.
From the 2. So that goes down here. And we got the 4 from the 2 as well.
Yes.
So this is what the traversal tree for using a queue right here looks like. We started off at 1, and then from 1 we got to 2 and 5, and then from 2 we got to 3 and 4. This is what's called a breadth-first search. Yeah. Does that smell great? Yes. That means that before we go to any children of new nodes that we've explored, we explore all of the different nodes we could get to from where we are right now. And this has the very useful property that the height of the node in the traversal tree that we've drawn here tells us how far that node is from where we started. So at the root, that's at distance 0. The next level, these are nodes that are right next to the root. At the next level, these are nodes that are 2 edges from the root, and so on and so forth. So if you want to look for how far nodes are between each other in an unweighted graph, you can do a breadth-first search by using a queue right here, and that tells you how far everything is. And you can see that by looking at the graph here. So here's our starting node. 2 and 5 are 1 steps away, and 3 and 4 are 2 steps away. Okay? So that's a breadth-first search. Let's see what happens if instead of a queue here, we use a stack. So again, we're going to start off at 1. We start off at 1. We pop the 1 off, and we push on. What do we push on again? What gets pushed on? What are neighbors of 1? 2 and 5. I'm going to put them in reverse order for reasons that will become apparent later. OK, what gets pulled off now? What's the next node we're visiting? 2. Comes off of this end now. So now we go to 2. We're at 2. So we've removed 2 here. And we're going to push on 3 and 4, right? So let's push on. And again, I'm putting them in reverse order. And then what are the next nodes we go to? 3. Where did we get to 3 from? 2. OK, so 3 gets removed. What's the next node? What gets pushed on? No, something gets pushed on. 4.
By the way, does it get changed?
What's that?
Does it?
Yes. I need to change that. Because we haven't been to 4 yet. We still need to push it on. So where do we go next? We go to 4. And we got there from 3. So this 4 came from 2. But this 4 came from 3. So our traversal graph looks like this. So the full traversal graph is just going to be a chain. We started here, and then we walked to 2, and then we walked to 3, and then we walked to 4, and then we walked to 5. So this is what's called a depth-first search. And that says, OK, we know that 5 was a neighbor of 1, but we weren't going to go down that path. We wanted to completely explore all of the nodes we could get through by following this first one. We wanted to go down this path first. And it turns out that we can explore the whole graph that way. We never had to go back and follow this edge. So we get a different path through the graph. So in general, depth-first searches are particularly useful because you can implement them very simply recursively. So if we keep the same visit matrix, we don't actually need to keep an explicit stack. Instead, we go to 1. We update our visited array and say, OK, we've been to 1. And then all we have to do is call the same search function, but now with a new node that we want to visit. We just say, OK, I'm going to now visit the depth-first node. I'm now going to call a depth-first search on 2, noting that I've already been to 1. I don't want to go back there. And then you explore everything you can get through from 2. And then if there's another neighbor that hasn't already been visited, then, okay, maybe there's a 6 over here. Then we would call a 1, and then recursively call a depth first search on 2. And that would recursively call a depth first search on 3. And you keep walking down here until you get everywhere. So you're still using a stack when you write it recursively like that. It's just that when you write it like that, you're using the function call stack in your compiler to hold the list of everywhere you're going. And so this implementation of it this way is a lot simpler because you can abstract a lot of that out. OK, so that is that's about as far as we're going to go today. Now we know what a graph is. We know how to generate a graph. We know how to turn a problem into a graph, right? And now we know how to explore a graph. And so that's going to be enough to solve this week's homework problem, which you can go and get started on. All right.